Welcome, ladies and gentlemen. Good morning. May I have your attention, please? Thank you. And so let's go ahead and take a look at the first Bellwork question. We're going to find the equation of the line tangent to a given function at a particular x value algebraically, and then we'll go ahead and graph them on the same screen. So I've got my emulator ready, and we'll take a look. We need the same three things that we've always needed, right? We need our x coordinate of the point of tangency, the y coordinate of the point of tangency, and the slope of the tangent line. Typically, we're given the first. In this case, x is -2. We can get that the y sub 1, the y coordinate of the point of tangency, by going to my original. So it looks like -2 quantity squared is +4. So it looks like the y coordinate is -1/4. Raise your hand if you had -1/4 for the y coordinate of the point of tangency. Great news. And then where do I go to find the slope of the tangent line? Right? Where do I go to find the slope of the tangent line? Courtney?
You find the derivative and then plug in the next value.
Absolutely, thank you. So we'll go ahead and generate our y. Y is given by -1/x². Then I'll go ahead and do the power rule. -1 constant multiplier. The current exponent on my power function is -2, so exponent times the base raised to 1 less. So that goes to the -3rd power times the derivative of the base is just plain Jane x. And so it looks like my y prime expression is negative times negative is positive 2/x³. We'll go ahead and evaluate. That looks kind of like x sub 3, doesn't it? So 2/x³. Sorry. Evaluated at my x coordinate of concern, that's -2. Gives me my slope of the tangent line. So -2 quantity cubed is -8. 2/8, I'm getting -1/4. And raise your hand if you had -1/4 for the slope of the tangent line. So hey, everything's working out. So we'll go to our point slope form and plug in our given values. So we've got -1/4 there, and we're all ready to go. So we know y minus y sub 1 is given by m times quantity x minus x sub 1. So we're using -1/4. My y coordinate, -1/4 for our slope, and -2 for our x coordinate. And it looks to me like we get y equals -1/4 x minus a negative is plus a +2 times the -1/4 is what? -1/2. Yeah. And -1/2 minus a 1/4 is -3/4. Is that what you're getting? All right. Now, we did not have to rearrange and solve for y, other than we wanted to graph on the same window to visually inspect our solution. And so you don't have to solve for y if you're just prompted for the equation of a tangent line, but I did so I could enter it into my y equals menu along with the original curve. Let's do that. Ooh, I like your lattice points, Mr. Fritz. Thanks, that was from our last time with differential equations. That's pretty cool. All about the format, baby. So let's go ahead and see. We've got -1 over, and we only need calculators today for our Euler's method, so it's good to have them out. So -1/x². In our tangent line, we got -1/4 x, excuse me, -3/4. And I don't know what a good window is. In fact, I don't know what my window was before, but I know the point of tangent is -2, -1/4. So I'm going to leave it and see what happens. -2, negative right there. Hey, looks like we've got our point of tangency. If I wanted to hop on the line, I could trace -2, enter, and jump on at -1/4 is the y coordinate. And then, as always, we could do our draw tangent command from second program draw tangent. And what do I want? At -2 is where I want it to draw. And we've got the cool line style overwrite. Gosh, that's gratifying. It even gives me a decimal approximation for what we calculate algebraically. So we're able to use a tangent line, right, at a particular curve. If we were to continue zooming in closer and closer to that point of that tangency, right, the tangent line resembles the solution curve more and more when we switch now to the arena of differential equations. So we're going to go ahead and extend this idea now of tangent lines and linear approximations. We're going to extend that to slope fields and differential equations, and Euler's method is going to be something we'll use to approximate that. But first, let's do one more with differentials. So we'll use differentials to approximate the square root of 4.1. Then we'll use our calculator to determine the error in our approximation. A couple of your homework exercises ask you about error, the difference between the actual function value and the approximation. So what are we going to do? Well, we need to choose, right? We need to choose some function y equals f of x. If I choose some function y equals f of x, I know my dy dx is given by f prime of x. And finally then, I know that my change in y, my predicted change in y using the instantaneous rate of change, the differential dy, which is what we're after. See how much, right, y changes, is given by f prime of x times dx. And so let's go ahead and choose a convenient function y equals f of x if we're asked to approximate the square root of 4.1. I gotta go with the square root of x. So I'm going to go ahead and choose y equals the square root of x. Then I know that dy dx, or f prime of x, equals 1 over 2 root x. And I'm going to use that to get an anticipated change in y, the differential dy, right, based on some small step over. Well, what small step over dx am I talking about? I haven't been given an x value of concern. And yet we can look at our original question, approximate the square root of 4.1, and choose a convenient x value that's close to what we're trying to approximate the square root of 4.1. So I'm going to choose x equals 1 as my x value. I'll use that to get my instantaneous rate of change. So if I consider x equals, 4, if I choose x equals 4, then my known function value is y equals what? So my known function value would be y equals 2, yes? Now we're going to go ahead and approximate, right, how much my y value would change if I were to step over a small step dx. Well, how much am I stepping over, right, for my known point? Marissa?
0.1.
Yeah, so my dx, my delta x and dx are the same thing. I'm stepping over 0.1. That's key for Euler's method today. We're going to be setting a step size, delta x, right, that will tell us how far we're going to be able to step over from our last known point on the solution curve. All right, so this is really a setup, right, for our discussion today. So what are we going to do? We're going to approximate dy. Dy, my change from that to, is going to be given by my instantaneous rate of change at my known point. That's 1 over 2 root 4 is 2, so 1/4. I should probably put that right here. Evaluated at 4 equals 4 is 2, 2 times 2 is still 1/4. So you're getting 1/4 for your f prime of x evaluated at, great, times, Marissa says, we're going to step over 0.1 units. Yes? So it looks like 1/4 times 0.1 might be easier just to go now with decimals because that's 0.1. So this is 0.25. And that's 0.1, so I can just move that over, right? Can I move that over one place and multiplying by 0.1? Yes? So that gives me an anticipated change in my y coordinate of 0.025. Yes? So our guess, right? Our guess is 2 plus 0.025. So we're guessing there's our approximation, right? You ready to see how we use differentials to get that? All right, now let's compare that with the actual. So we'll just do our regular calculator, home screen. And we're going to go ahead and do our actual by doing the square root of 4.1. How well did we do? looks like, hey, we did pretty well. And so the actual value, the actual value, correct, 8 places, is, that's forever without stopping and falling to a repeating pattern, irrational, is 2.024845673, right? Compare that with our anticipated, and we're talking about not too shabby, so that's 0.1230, right? 0.000154, so that's pretty good. All right, so our error is only 0.00015, and that's not too shabby. Awesome. What question do you guys have about our Bellwork today? That's a great setup for today's discussion. So let's go ahead and take care of our OTL, and I'll pause the recording, and then we'll get going. All right, so ladies and gentlemen, we've been dealing with slope fields, right, and seeing how they're a visual representation of a differential equation that will provide us the instantaneous rate of change of a family of solution curves, right, or a particular solution curve should it pass. Should it pass through a nearby point. And so here we can visually see kind of the family of solution curves without knowing the differential equation, right, and without knowing the solution curve, we can kind of see what the family of solution curves would look like. In general, what does it appear, right? How does it appear that the family of solution curves kind of resemble, just by looking at it informally? Tyler?
Circles.
Yeah, it looks kind of like circles. It might be an ellipse. You know, it's hard to tell if on major axis or minor axis with circle. No, absolutely. And so we don't know, but we can get a visual representation of what the solution curves might look like by looking at the graph of the slope field that the differential equation produces. All right, so what we're going to do first is informally, all right, go ahead and approximate a particular solution curve that contains a given point just by drawing. So we're just going to sketch, right, visually, and we're going to pretend that -2, -1, and I changed the coordinate here, so I just want to make sure. -2, -1. Okay, so I changed this on your note sheet later. So everybody, -2, -1 is where I want to start. So let's go ahead and start at -2, -1. And we're going to go ahead and see if we can't sketch in. So -2, -1 is about here. Pretty good. And now we're going to go ahead and we're going to sketch in what the particular solution that contains that point would look like. And again, this is an approximation. I'm thinking it's going to look something like this. Horizontal here. I don't know. It's tough, all right? So good. A little better. Okay, so, right, that is just an estimation. It's just a sketch, okay? Now, I did my best to follow kind of the signposts that each mini tangent line, right, each little line segment pointed my solution curve in, and pretended like I was dropping that proverbial leaf in my current in the river, right? And it was taken by the current in different ways depending upon what the nearest direction looked like. All right. Now let's use our sketch to approximate f of -1. What? Well, now let's pretend that we're on that solution curve, all right? And we want to estimate the value of the function when x equals -1. Can we do that? Well, sure. Let's go ahead and jump on it. So I'm going to go at x equals -1, and I'm going to jump on the function, and I'm going to think what function value is produced. So what do you guys think? -1.5? What about you guys? Yeah? Samesies? All right. So let's go ahead and write it down. We're going to say about. We're going to say about -1.5. All right. I don't know if that is or isn't. But we're going to say about -1.5. Then we're going to see how we're doing it. All right. Now, Euler's method uses instantaneous rate of change at successive points, right, to predict the path that the solution curve would take. Instead of us just visually doing it by hand when we're sketching, it's going to use actual instantaneous rate of change values with little mini tangent line segments and push that leaf along, right, using the last known slope. Then, after one step, right, it'll now calculate the instantaneous rate of change at my new point, reset my direction and push that leaf along again, right, using the instantaneous rate of change at my last known point. And so by doing this, it readjusts, right? But mathematically, to continue pushing that leaf along using the last known slope value. All right, so it's going to, if I were to jump on -2, -1, we know that value. It's going to perform a slope calculation using dy dx, right? And then algebraically push that along a given step size, I've already said, according with the last known slope. Then it'll take this new one in blue and it'll do a slope calculation, redirect based on the new instantaneous rate of change, and it'll change direction slightly and then push that along, right? Another step. Now I'm at the red point, and it'll do a instantaneous rate of change, a slope calculation using dy dx, and readjust using the last known point, and so on and so forth. And so by this, it's doing exactly what we were doing informally, bless you, exactly what we're doing informally with our sketch, but doing it mathematically, right, using instantaneous rates of change. Now, it's still going to be approximation because we're still going along a straight path for that little delta x step, like differentials and like tangent lines. But if we have a smaller step size, right, then we're going to get a more and more accurate approximation. So let's go ahead and see if we can apply this mathematically and see how well we did, right, when we did our approximation visually. So I want everybody to change your point, because I made this before, then I made that. And so everybody add a negative. We're going to start at -2, -1. It's supposed to match the whole time. So we're all doing -2, -1. Does everybody have it? So we're going to start at -2, -1. And we're going to use Euler's method with step size of delta x 0.5 to approximate f of -1. So we're going to go from x equals -2, where my y value is -1. And we're going to go to figure out what the y coordinate, right, approximately is when x equals -1. How are we going to do it? Well, we're going to step. Right, we're going to use our delta x step, just like our dx from Bellwork. We're going to step over 0.5 units and use the calculated instantaneous rate of change from the previously known point to push that leaf, right, in that straight line mini line segment, and then do a recalculation, reset my compass, and push again, right, in my new direction based on the instantaneous rate of change. So we'll always start with our known point, x comma y. I tried to make kind of the setup for our little table. I didn't fill in these vertical lines. You can, but I wasn't sure how much space we're going to need, so here we go. -2, -1 is my last known point. In fact, that is on the solution curve, so I know that to be on the solution curve. Now I'm going to go ahead and calculate dy dx, the value of my slope, right, my instantaneous rate of change at that point. How will I do that? I'll simply plug it into here. So that'll be opposite of, my x value was -2, my y value was -1. Is that right? So it looks like my slope value is, I'm going to scooch that one more. So it looks like my value of slope line is 2 over -2 is -1. I got you -1?
Yep.
Awesome.
Wait, yeah.
Yeah?
Yeah.
-1?
Sorry.
Sorry. It's okay. All this together, high school musical style. My delta x we were given, we're going to step over 0.5 units. So my delta x is 0.5 units. So my anticipated change, right, my anticipated change in the y coordinate, based on my step size of 0.05, no, I'm sorry, 0.5 rather, is given by my instantaneous rate of change, which is calculated to be -1, times 0.05. So I anticipate a change of how much? I anticipate a change of -0.5 units after stepping over 0.5 units, right? You guys see that? So what does this affect? This affects my y coordinate and gives me an approximate new point for the solution curve. So I'll increment now my x and y coordinates based on how much I stepped over delta x and my anticipated change dy from a differential. Here we go. My new point, dun, 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 before I restart the process then, becomes -2 plus 0.5 units over becomes what? -1.5, comma. My y coordinate, we anticipate changing from -1 down another 0.5 units would be -1.5. Yes? Awesome. And now I begin the process again. So my new point that I'm starting with, right, is an anticipated negative 1.5, negative 1.5. I'll now calculate my instantaneous rate of change using dy dx. That's opposite of my x coordinate over twice my y coordinate. So for us, now that's opposite of negative 1.5 over negative 1.5. And now my slope field predicts, right, an instantaneous rate of change of what? Negative 1/2? Negative 1/2, yes? Are you guys getting it? What's my delta x? 0.5 units, so that's still 0.5. And so my anticipated change, dy, is given by my instantaneous rate of change at that point. We calculated it to be negative 1/2 times my delta step, dx, is 0.5. So I have 0.5 times 0.5 is an anticipated change in my y coordinate of what? 0.25 down, right? So negative 0.25. Are you guys getting that? All right. So after two, right, iterations, we've gotten from x equals negative 2, right? One step to negative 1.5. Next step, another 0.5 units. So our new point would be what? What would our new point be?
Negative 1.75.
Yep, negative 1.75 is my y coordinate. So how do we do with our visual? Well, we don't know because this is an approximation and so is that, right? And so we've used Euler's method twice with a delta x step size of 0.5 units. We've stepped over, right? We've stepped over 0.5 units, and now we've gotten to x equals negative 1. We've accumulated change in our y's using instantaneous rate of changes, and we're getting negative 1.75. Are you guys okay? Are you guys getting this?
Yeah.
Everybody good? All right. So we've used Euler's method with a relatively large step size of 0.5 units to get an approximation for my function value when x equals negative 1, and we're getting negative 1.75. All right, so there's our visual. There's our setup for Euler's method. There's our Euler's method, and now, all right, excuse me, this is a computer program that you can set your delta x step size. And as we do that, does it look like our visual, right, with our sketch was better? Or does it look like our Euler's method? Well, this is Euler's method, and so it's going to give us the same. We got 1.75, negative 1.75. All right, now the moment of truth. In this particular differential equation, right, could we solve that algebraically? Uh-oh. We need a negative 1 here, don't we? So can we solve this differential equation algebraically?
Yes.
You bet your boots. That's separable. So we can, if we can separate my variables through multiplication or division, right, to get all the x's on one side and all the y's on the other, then we can find a particular solution if we know, right, if we know an initial condition. Let's do that now. So we'll go ahead and multiply over. I'm just going to do the y and leave the. Are you guys okay with that? I'm just going to move the y so I have less business to solve for at the end. See what I'm saying? Save time and energy at the end. I'm just going to move the y over because I have my choice of what I want to move to multiplication division. I'm only going to move the y over so that I have less to solve for after the fact. Remember, a particular solution I'll solve for y at the end. So if I just multiply over y, I got less work to do at the end, hopefully. Next, opposite of x over 2 dx. You guys good? And now we're ready. So let's go ahead and find a particular solution that contains my initial condition. By integrating both sides, I generate an antiderivative on the left and get y squared over 2. On the right, I get negative x squared over 4 plus c. Is that what you guys are getting? Yes, plus c. Are you good? Okay. And we have the option. We could solve for y first and plug in my initial condition last, or we could plug in my initial condition right now, right, and solve for c right now and then solve for y last. I kind of like solving for y first and then plugging in at the end, but the choice is yours. So I'm going to go ahead and solve for y first. I'm going to clear the fraction on the 2 by multiplying everything by 2 both sides. Therefore, y squared equals, it looks to me like I get negative x squared over 2 plus, and this constant c times 2 is still some constant c that I don't know. And so, right, we could call that 2c, or we could simply call it c, because it's still a constant that I don't know. So it's okay, right? It's okay, since we haven't plugged in an initial condition, to let that remain an unknown constant c. Now I'll solve for y by taking the positive and negative square root. So I'm getting y equals the positive and negative square root of c minus x squared over 2. And now I'll go ahead and consider my initial condition. Which branch, right, which branch, the positive or negative square root, is going to include this point, negative 2, negative 1? Right? I've got a plus or minus here. Which branch is going to contain the point negative 2, negative 1?
Negative.
Yeah, the only way that this, right, is going to produce a negative output value is if there's a negative out front. And so this is where we purposely grab the negative one, because my initial condition is negative 2, negative 1. That's the point I'm going to use. So I know that my particular solution is the branch, right, that utilizes the opposite square root. So now we'll go ahead and plug in. Here we go. The particular solution then will be given by negative 1 equals opposite of square root of c minus x squared was negative 2, quantity squared is 4, minus 4 over 2 is minus 2. Multiplying both sides by a negative produces positive 1 equals positive root c minus 2. Squaring both sides produces 1 equals c minus 2. So I'm getting c equals 3. Are you guys doing that? C equals 3. It's pretty long, you know? Which means that my particular solution, y, is given by the opposite of square root of 3 minus x squared over 2. Alright guys, we wanted to know how good of a job Euler's method did in approximating the value of my function when x equals negative 1. So let's use our particular solution curve and evaluate when x equals negative 1 and see how we did. So we'll go ahead and rewrite this. If we evaluate this at x equals negative 1, I'm getting square root of 3 minus the square root of 2.5. Is that what you guys are getting? 1, negative 1 squared is positive 1. 3 minus 1/2 is 2.5. Yes? So what is this giving? I don't know. I don't know. Opposite of square root of 2.5. Negative 1.58. So we are too low. Well, that's disconcerting. Well, not really. We use a step size of 0.5 units. So think about how we could make this approximation better. Well, that seems pretty cruddy. Which method was better, right? Was it the drawing? Was it Euler's method, or was the particular solution? Well, that's no brainer. The particular solution gave me the exact value. However, sometimes we don't have an algebraic method yet to solve my differential equation in particular. Consider a differential equation y minus x and the slope field it produces. Are we able to separate the variables through multiplication and division to solve that? At this stage in our lives, no. And so Euler's method is going to now give us a way that we can mathematically approximate function values based on the differential equation and slope field when we're not able to find a particular solution. Tyler?
Are we going to learn that this year?
No, not this year, but you will in DiffEQ.
What?
Differential equations in college. A whole course, a whole semester course. Yep.
Oh.
If you take math in college, a whole semester course, right? A whole semester course devoted to solving differential equations.
Of course.
All right, so let's go ahead and take a look at this slope field. Guys, check it out. let's suppose that we know the point 1, 1 is on the solution curve. So everybody, let's jump on my curve at 1, 1. Yes, about here. Can we guess then what would happen if we were to try and sketch the particular solution that contains that point? Yeah, it looks to me like we're leveling off here, aren't we? And I would guess like this. Maybe. Maybe. Minus that last part. Is it okay? Yeah? Also minus? That's tricky. It's still a hard time because it's not, you're just visually trying to follow the signposts. All right, now let's use our sketch to approximate f of 3. So we knew this point was 1, 1. That's on the solution. What about when x equals 3? So when x equals 3, oh gosh, that's all the way over here. So let's go ahead and see. Right here? Right here? So what are we guessing? What are you guys guessing?
2.75. Negative 2.75? Negative 2.
I'm down, Tyler. I like it. Let's go ahead and see. All right. Let's go ahead and see what our method predicts. So we'll go ahead and consider a starting point of 1, 1. And we're going to go ahead and utilize Euler's method as a means for approximating f of 3. I just want to scooch over a little bit, so we're going to make it. All right, guys, let's take a look. So we know our start point is 1, 1. Now we'll calculate the instantaneous rate of change at my known point using my differential equation. So my instantaneous rate of change at 1, 1 is 1 minus 1 is 0. Everything is 0? Oh, this will be fast. What's my step size? 0.5. So my anticipated change dy is given by 0 times 0.5 equals 0. Great. So what's my new point? When I step over 0.5 units in my x-coordinate, my predicted change in the y-coordinate is 0. So what's my new point? So, yeah, 1.5, comma 1. Good. Very nice. This is good. So my predicted new point is 1.5, comma 1. Excuse me. All right. Now let's use my new point to calculate my instantaneous rate of change using the differential equation. So I get 1 minus 1.5. That equals negative 0.5. Is that what you guys are getting? Multiplied by my delta x 0.5 produces my predicted change in y coordinates. Negative 0.5 times 0.5. So what are we predicting for our next one? Negative 0.25. Yes? Yes? Negative 0.25. All right. So what's my new point? Increment my x-coordinate, delta x units, and then take my anticipated change dy and increment my y-coordinate. So I'm now at 2. I'm now at 2, comma, what? 0.75? You guys good? Awesome. All right. So we're seeing now the iterative process. We'll go ahead and continue making calculations using my anticipated point. Now my new instantaneous rate of change is given by y-coordinate 0.75 minus x-coordinate of 2 produces instantaneous rate of change of what? Negative 1.25. I'm about to go to my calculator now. So my dy is given by negative 1.25 times 0.5 equals negative 0.625. You get that on your calculator? Yeah. New. Hey, I made it farther than I thought I was going to do. Increment, x coordinate, y coordinate. We're closer, you guys. I think we're all the way to 2.5. Almost there. Aha! So, oh, everything was going so well. 0.125? 0.125? What was you guys getting? You guys get that? I'm doing non-calculator so far. I'm impressing myself. So now I feel like it's a challenge because I'm at 2.5 already. All right, so what are you going to do now? Oh, challenge lost. 0.125 minus 2.5 equals negative 2.375. Yeah. You can see how I spent my icy road conditions today. We're gonna be confused. When's your lesson? So then, looks like negative 2.375. No idea this one. 0.5. So the last one, you'll have to help me on this. So what did you guys get for this? You ready? Marissa?
Negative 1.1875.
Nice.
Gosh, we're close. So what's my final prediction? All right, we're gonna see. It's gonna be way less than that. We must have gone left. Well, I want to see what happens here. So we're guessing 3, comma. I must have made a bad drawing. Oh gosh. All right. 0.125 minus 1.1875. What do we do? Negative 1.0625. What do we predict? Oh my gosh. So here, okay, well, so I see what happened though, because the first slope was 0, so it kicked out here half unit before curving down. So maybe ours is over here. Let's go ahead and take a look. So what could make a better approximation than negative 1.0625? Well, if we had the time, right, and the energy, and did some taping just on the digits for reinforcement, because we'd be doing a lot of calculating, right, we could do more than the 0.5 unit step size. What if we considered and went by 0.25? And so we don't have to do this. What I did is I used the computer program, I know, to show, look what happens. And now look at my y-coordinate. You can visually see that my y-coordinate, right, is closer in line to our intuitive. So which step size produces a more accurate result? 0.5 or the 0.25? 0.25, full show, right? So you can see that. Even when algebraically you don't have the means for solving. Perhaps a more interesting question though is why, right? Why does the smaller step size produce a more accurate result, right? So besides the picture. So yeah, we can see that. So what would we say in terms of calculus? Okay, so go ahead and turn to the person that's close to you, since we're not in partner formation. Pick someone close to you. Why does the smaller step size produce a more accurate result?
So you were thinking, Brendan?
Oh, yeah.
Me too. Let's go. That's teamwork. Marissa, you too?
All right. Go ahead and share with the whole class then what you guys said when I call on you. So, why does the smaller step size produce, right, a more accurate approximation? Riley and Kobe?
Because it would check itself and recalibrate in your slope more often.
Oh my gosh, Riley, I was going to use the same word, recalibrate. It's like we recalibrate our compass more frequently, right? We recalibrate our compass using the exact differential equation more frequently so that we can stay on a more accurate path. Absolutely. Recalibrate. Awesome use of language, dude. All right, let's go ahead and close up and then get some more trail time. So given a known point x comma y, explain how to determine the approximate coordinates of a new point after moving just one step using Euler's method. So just I want to know one-step process, what is it you do procedurally? Second, what part of Euler's method can be changed to provide a more accurate approximation for a particular solution value? I'll pause the recording just for a moment and then we'll go ahead and share. Go ahead and share with the class then how to get from a known point x comma y to a new predicted point using one step in Euler's method. What is it that you do procedurally, right? What do you do procedurally? Marissa?
You multiply, well, you find dy dx and then you multiply it by the change in x.
Absolutely. You use your known point x comma y and plug it into your dy dx, evaluate it at x comma y, right? And then that gives you your anticipated change in y. You'll then add that on to your y value and increment your x coordinate delta x steps to get your new point x comma y. Excellent, thank you. What part of Euler's method can be changed to provide a more accurate approximation for a particular solution value? What do you have for that, Emily?
Delta x, and you can use a smaller delta x to allow for more recalibration.
Nice. So you can make my step size delta x smaller. Right, you can make delta x smaller. And that will provide for more frequent recalibration and slope calculations as you continue to push that boat along in the proper direction. Right? Absolutely. You guys are awesome. So please listen carefully. I wanted to make sure you had some time, but I did put a couple sketches at the end, right, because I thought they were interesting, particularly with perpendicular slopes. And so think about what does it mean for two lines, for two slopes to be perpendicular, what would be true about their values? Right, two slopes, opposite reciprocals now help with some of the end ones. The first ones are Euler methods, and a couple of them ask you to step backwards. And so we do the same thing, we just be walking from right to left as opposed to walking from left to right. Awesome, you guys. I'll go ahead and post the recording on my